Thank you for coming. And it is with my great pleasure that I am introducing Stefan Bäuml, who is currently postdoc with Tony as seen in ICFO, and he is here visiting us yesterday, and today will be giving talk that he worked with Andreas Winter and Donnie, and he is good with private estates, QKD, over network. So if you have any questions or something, you can always talk to him. So yeah, Stefan, you may.
Yeah, thanks, Siddharth, for inviting me here. I'll be talking about entanglement-assisted classical capacity, and we have shown that every entangled state can provide some advantage in classical communication. And as Siddharth says, this is joint work with Andreas Winter and Don Young. Okay, probably know a lot about this, but I thought I'd just give some short introduction first into just classical communication via quantum channels. So the idea is that we've got some classical message. Actually, this was supposed to be dashed. I think it doesn't. Yeah, it doesn't show dashed here. It should be dashed. So we've got some. Okay. Thanks. Oh, it's okay like this. So we've got some classical message here. Then by Alice, so Alice can perform some encoding operation. And then we have a quantum channel that goes from Alice to Bob, and this can be used many times, let's say n times. And then Bob performs some decoding operation, and this should give him some guess of the message, which should contain little errors. And then one can define a capacity basically as the maximum achievable rate. But maximum is basically over all those encoding and decoding protocols. And this M here is size of the input alphabet, and N is number of channel uses. Okay, one can also take the regularized, or take the asymptotic limit here. And then in general, we could have create one big quantum state here that might be entangled between different uses, but one would of course be more easy if we have tensor products of multiple quantum states here. And if we have such a product encoding, we can achieve this rate here, which is the Kolevo capacity, okay, of the channel, which is defined like this. It can be defined as a mutual information of this classical quantum state here, where we have a maximum over all possible input ensembles. And then it's well known that if we regularize this Kolevo capacity, we get the classical capacity of the quantum channel. But of course, there have been some examples where this here is not additive, so it's in general difficult to compute this capacity, but easy to compute the Kolevo capacity, which gives us a lower bound on the capacity here. Okay, now what one could think is, does it help if in addition to the quantum channel, Alice and Bob have some additional entanglement? So there one could think of different scenarios. One would be that we have many, for example, many copies of pure states here. And in this case, actually I think so it has been entanglement assist, so-called entanglement assisted classical capacity has been defined where I think they even allow for unbounded amount of pure entanglement here. And then we can also define the capacity analogously. And there's actually a very nice theorem which has been shown already 20 years ago, that this entanglement assisted capacity is just the maximum mutual information of, we maximize all pure input states over this one here. And what is very interesting about this quantity is that we don't need the regularization here. So this is actually like a, let's say, single letter result. And this is very well known and very old. So, but what we were thinking was something different. What happens if we don't allow for pure state entanglement here, but let's assume we have some mixed state entanglement here, so some noisy entanglement. Of course, one thing one could think of is, so far we had a noisy channel. Let's first assume we've got an identity channel here. Okay, if we have just some channel state here, but if the channel state is Bell state and is an identity channel, then of course we can just do quantum dense coding. So this is also like very well-known protocol from 1992. And then it has been shown, this was also 20 years later actually, by Hordetsky, forgotten who, Pavel or who it was, and Marco Piani. They have shown that, let's assume we have some mixed state here, but we have the identity channel. And in this case, they've been shown that we can always get an advantage when the coherent information of this state here. I mean, here we assume we have one state per channel use. So, and they have shown that whenever the coherent information of this state is strictly positive, then we can get an advantage. So they have some analog, something like dense coding, but the state is noisy. And also what is known is that there are entangled states which are entangled but which have non-positive coherent information. And of course, it's for those we cannot get an advantage if we have the identity channel here. But what we were thinking about, maybe we could still get an advantage if we don't have the identity channel here, but we have some other channel here. So basically what we're considering is we have a noisy channel here and a noisy state here, and we want to see maybe this combination can still give, in this combination we can still get an advantage even for some states which have non-positive coherent information. So in general, we can just define a capacity like this. So we've got some noisy state row here and some noisy channel here. Then we just, in here for simplicity, we always assume we have one state per channel use. So we can define this row-assisted classical capacity of the channel just in analogy to the other capacity. And then we are not sure if this is always true, but we have some partial results going in that direction. So Andreas at some point had the idea maybe one could conjecture that for any entangled state, which of course includes the entangled states which have non-positive coherent information, that there exists some channel such that the row-assisted classical capacity is strictly larger than the normal classical capacity of the channel. And of course, yeah, this is interesting for those states here, because for the other one, we can just use the identity channel here and then use the result by Hordetsky and Piani. Okay, and then let me briefly talk about bound entanglement. Apparently, what I've been told is maybe 10 years ago or so, this was, or maybe 15 years ago, this was a very interesting topic which everyone knew, but someone told me it has come out of fashion to think about bound entanglement, so maybe younger people don't really know anymore what it is. Basically, the idea is that if we have some state row, and then if we can, if we have many copies of the state row, and by LOCC we can transform it into some number of copies of a maximum entangled state, then we say that the state has a distillable entanglement or is distillable. And now there are states which are entangled, but we cannot use them to distill maximum entanglement from them, even if you take many copies and take arbitrary LOCC operation. And those states are called bound entangled. So formally one could say if the entanglement cost of the channel is larger than 0, which is true for any entangled state, and the distillable entanglement is equal to 0, then rho is bound entangled. And it's also known that if we have that for any bound entangled state, the coherent information is less or equal to 0. This is actually also true for states which can be distilled to maximum entanglement, but only by two-way communication. Basically, they cannot be distilled by one-way communications. So bound entangled states and those states which are not one-way distillable are, as we showed before, useless for this dense coding result by Piani and Horodecki, but it can still be entangled. And then, also some time ago, people were interested in bound entanglement, so it has been shown in this paper by the Horodetskis and Jonathan Oppenheim that bound entanglement can be used for quantum key distribution. Then there has been this result by Luis Mazanes that we can increase the singlet fraction of some other state, which is not bound entangled, but if we add some bound entangled state, we can increase the singlet fraction. And then has been shown by Tamas Vertesi and Nicola Brunner that there are bound entangled states that can violate a Bell inequality even. And this is something we've shown some time ago, that bound entanglement is probably useless in a quantum repeater. So this was kind of some time ago that people were interested in what bound entanglement can be used for and what it cannot be used for. And we kind of carry on in this direction, and we're interested in if bound entanglement or entanglement which is not one-way distillable is useful for classical communication. Okay, and for our result, we borrow some other result which has been shown by Marco Piani and John Watrous, which shows that any entangled state can provide an advantage in channel discrimination. So let's assume we've got two quantum channels, M1 and M2, and then we are interested in their trace distance, which is just where we maximize our input states, and then look at the trace distance of the output states. And if we allow by assistance by some bipartite state rho AB, we did just define it like this. So basically, let's say Alice sends has the state AB and sends part of it into the channel, and the other part is just sent to Bob, and then Bob tries to distinguish between the output states. Actually, I think if we would maximize over, I think as far as I remember, if we maximize over all those, we would get the diamond norm, but here we don't use the diamond norm. And then it has been shown by Piani and John Watrous that for all entangled states, so this of course then also includes bound entangled states, there exist two channels, M1, M2, such that this rho-assisted distance is strictly larger than the unassisted, the trace distance. And basically, the idea we had was to somewhat use this result to construct some channel so we can show our conjecture, but we only got partial results. So what we could show is, okay, that's just a small thing that can also be entanglement breaking. But what we could show is that we can construct some kind of memory channel such that the feedback assisted classical capacity with product encoding can always be increased by the state. So maybe let's just briefly slowly explain our idea. So we assume we have some scenario like this here. So let's say we've got Alice here and Bob here, and then let's assume they have here they're presented with M0 and M1 are the two states which are given. I mean, for a given state, let's say that M1 or M0 and M1 are the two channels that exist by the paper by John Watrous and Marco Piani, which can be more easily distinguished if we have the state. And now we assume that we have a setup like this. So there's we have some random number here, 0 and 1, which then, depending on this random number generator, we either have M0 or M1 here, and then this choice is saved in the channel. So we could see this as something like a memory channel. And then we have correlations between those two channels and this channel here, this N0 and N1, those are classical quantum channels which consists of measurements in two different mutually unbiased bases. So basically, if we have a 0 here, then this channel here will be the M0 channel from the Vatros-Piani paper, and this here will be a measurement in the basis V0. And if we get a 1 here, then we have the other channel here and measurement in a different basis. And those things are always correlated because we have this like internal memory between those two channels. So this entire thing we can call a memory channel. And the idea is that that this here is random. So basically, with probability 1/2, we have a 0 here, or with probability 1/2, we have 1/2 here. And then the idea is that if they want to use this for communication, then Alice could first send some probe state through this part of the channel to Bob, and then Bob has to try to learn the value of this bit here, of the 0 and 1 here. And for this, he can do better if he has this additional entangled state. This is the result by Vatros and Piani. But then one thing is, he has the result here, but then Alice needs the result for encoding. So he has to do some classical backward communication, just send some message back to Alice, and then if Alice knows his guess of the channel, she can encode in the right basis here, and she can get more information through here. Because of course, if she doesn't know which basis the measurement is here, she cannot get much information through. But if she would know exactly probability 1 which basis would be measured here, she could just encode the message in the corresponding basis. And then the idea is also that, so basically, the idea is that the capacity depends on how good Bob can distinguish between those two channels here. And then also we had the idea, of course, this could be the advantage for some given state might be very small. So the idea is that we also show that even if the advantage is very small, we can just choose this dimension D here large enough, such that we can even amplify the smallest advantage we can get here. Okay, and then more formally, we define this as a quantum memory channel, which looks a bit ugly, but there's been some theory on quantum memory channels by, I think, Werner and someone else. Basically, in the memory channel, we have some, so A and B are the normal in and output register, and then this one here, I and K, those are some additional classical in and output register which correspond to the memory. And then in the memories originally set to basically set to some random value 0 and 1. And then after every second round, it's reset again to 0 and 1. So I think they call this has a memory of 2 by the notation of Werner. And then here, basically, we also have this case, basically just an even odd counter that in every round just changes between 0 and 1. And then depending on if we are in an even or an odd round, we have either channel M here or the channel N. Yeah, and exactly, and after every odd round, the memory is reset again. So this is the channel we are using. Yeah, this is exactly the I correlates them, and that's an even odd counter. And then what we compare are those two capacities. One thing is we had some technical problems why we only show this result for capacities with product encodings. And then this here basically means that we allow for feedback. So it's the product encoding feedback capacity. And this is if we allow rho in addition. So we define those two capacities here. And then we show that for any entangled state and large enough D, we can get that for this memory channel here, we have that the assisted capacity is, the rho assisted capacity is strictly larger than the unassisted capacity. And this we show, let me just give you some outline of the proof. So in the first step, we upper bound this part where we don't have the row assistance. And this we do, first we define some kind of Holevo capacity for every n after n rounds. So let's say after, and this is defined, let's assume this is like our protocol. So we have this random number generator here, then we have this correlated channel. Alice sends something here, Bob performs a measurement, that's the backward communication, which she uses, Alice uses for some more encoding and so on. Then here Bob performs another measurement and so on. And if we look at the CQ channel, I think the first one would be just after the channel use. Then the second one would be here, where we have Bob has performed a measurement, sent something back, and then Alice has performed the second one, but before this measurement has been performed. So we, let's say, for round one, we would have the CQ state here for the Holevo capacity number 1, and then for 2 it would be here, for 3 would be here. And then we show that for every even round, so it would be, for example, what would be even, like this would 1, 2, so would be, what would be here for, would be here and here. So for every even round, we can show that this Holevo n plus 1 is less or equal than Holevo n plus this term here, this mutual information. So x is just from the CQ state, like from the input, classical input. And then we have the conditional mutual information between like this input alphabet here and output b n plus 2. So this would be, for example, b2 here or b4 here. And then we condition on the here on b tilde, b prime is always after the measurement by Bob here for the previous round. So we would have the mutual information between x and this one here conditioned on that one, or for the next one we would have it x mutual information with this one here, b4 conditioned on b, on this one here, on b prime tilde. And then here we get some term of log, and this is the dimension of this channel M here. This of course depends on the state, because this depends on how they construct it in the paper by Watros and Piani, but the idea is that we always choose dimension here large enough that we can neglect those terms. Okay, I mean here we do some induction proof, but I don't really go into the details. But one thing we use when we want to prove this is that for every even n, b, n plus 2 is always the output of a measurement of two mutual unbiased bases, like here b4 or b2. This would be two mutual unbiased bases, so we can always apply this entropic uncertainty relation. So this means that the entropy, if we measure in one basis, plus the entropy if we measure in the other one, is always larger or equal than log d. And this is one key ingredient we use in this proof here. And so, yeah, basically, so we can then upper bound, lower bound, I think this one here, and in any case, this allows us to show this upper bound here. So what we still have to show is, so remember that this here is, in the upper bound, we get this normal trace distance between, basically unassisted distance. And then next we show a lower bound where we have the row assisted distance here. And there basically we just do this kind of protocol which I've described before for the lower bound, where we have assistance. Basically Alice just enters part of the state here, and then Bob performs some measurement to guess which of the two channels has been used here. And then he has this guessing probability, which of course depends on this row assistant distance. And then Alice can encode in, depending on the guess, in some neutral unbiased basis. And then the transmission probabilities are this, so this at some point just reduces to classical symmetric channel. And then we can get a capacity given by this term here. And remember that the delta here is given by this row assisted distance between the two channels. So we have, so then we can get that one, and if we combine this with the upper bound we have shown before and use a Piani-Vatres result, we can show that actually this row assisted capacity is strictly larger than the unassisted if we choose D large enough. So now, of course, it's nice we have shown that any entangled state can increase the feedback assisted product capacity of some memory channel. But of course, this is like not nicest example. I mean, it's interesting, but of course, it would be nice to have to show the original conjecture where we wouldn't need to have this feedback assistance here or the product encoding, and we would just have the normal channel instead of a memory channel. But in this case, we couldn't show it in general, but we could just find some examples. So what we found is some example of a channel and of a state which is not one-way distillable, where we can still get an advantage in classical communication. And that advantage is just in a normal capacity. So this is like second approach. And for that, we borrow some idea by old paper by Peter Shore. And I think in this paper he shows equivalence between different additivity questions. I think, for example, he shows, I think that equivalence of the minimum output entropy is somewhat equivalent to, I think, what was it? The additivity of the Holevo capacity. And here, and in here is made such as a channel construction here. So basically, it's assumed we have some channel M A to C here, and then we just consider this larger channel N, let's say call it N index M, where we have an additional input here, which is dephased, and then used as a control for some random unitaries here. And then we discard that one and get that output here. And what is interesting about this channel because this here just gets randomized by those unitaries here, we get that the Holevo capacity of the entire channel is given by log of the dimension of this output C here, so minus the minimum output entropy of this channel. So I think this is just, if we use the other definition of the Holevo capacity, we can see this because we have, I think, what is it, the entropy, just, let's assume we have some input ensemble here, and then we have the entropy just of the entire output state. And of course, if we choose the right input ensemble here, this can just be that we get the maximal entropy here. And of course, in the Holevo capacity, we have to maximize. But here we have basically the convex sum over the entropies for every state in the input ensemble. So here we can just then choose a state, for every state here, we can just choose the state that minimizes the output entropy of this channel N, of this channel M here. And then this is just basically, so we don't have the convex sum inside the entropy, so it doesn't matter that we have a unitary here. And I think this is also what he uses to show those additivity questions between Holevo capacity and the minimum output entropy using this channel construction. But then what we could show is that a Collivo capacity where we have row assistance is actually larger or equal than log of this output dimension here minus the conditional entropy C condition on B of omega, and omega I think I haven't written here. So basically omega, let's assume we've got some state rho AB like the state we are interested in, we want if it can be a system. So we've got rho AB here, so we've got a system B, and then after applying M, we call this state here omega. So basically this is the state if you have rho AB and then send a system into the channel M, then we can get the state omega here. And then if you look at those two things, we see that if this conditional information is strictly less than the minimum output entropy, then we get that there's also a strict difference in the two Collivo capacities. And if in addition the channel is entanglement breaking, for entanglement breaking it's known that the Collivo capacity is additive. So for the capacity is additive. So for entanglement breaking M, we even can show that we can get an advantage in the capacity here. And now basically what we have to do is just find examples where this here is fulfilled. But of course one problem is that the minimum output entropy is something which is difficult to compute. So we're looking at some examples where the minimum output entropy is known. And then we found combination of states and channels where actually we can get an advantage. And those are one is the 2-qubit Werner state defined like this. And this is known to be one-way undistillable for this parameter region here. And for the channel we use this transposed depolarizing channel, which is basically like a depolarizing channel, but then here we perform a transpose. And for this, the minimum output entropy is known. And then here we made a plot where we compare the two entropic quantities, and here in this blue region we can this one here becomes negative. So here we know that we can get an advantage in classical communication, even though the state is one-way undistillable. So this was our example. And then another thing we noticed, what is also interesting, is that this condition we just had, where we compare the minimum output entropy and this conditional entropy, this can also be seen as an entropic entanglement witness. So basically, using the strong superadditivity, one can show that if we have some channel M from A to C, the minimum output entropy is the minimum over all separable input states of this conditional entropy here of the output state. I here now this finally have written the omega, which was missing before. And so of course, so this is the minimum over all separable, but if we have some state where this quantity here is less than that, then we have to know that the input state has to be entangled, because it cannot be separable, because like this is the minimum allowing for separable inputs. So we know that if we have something like this, then we know that rho has to be an entangled state. And this can be called an entanglement witness. I mean, it's not a linear witness, but some people also call such a condition an entanglement witness. And basically, classical communication, this would be like an operational interpretation of this witness. So we show that the state can provide an advantage in communication, which this is something, of course, separable state cannot provide an advantage. And so we know that the state is entangled, and we have entanglement witness. Okay, that's it. Thanks. Questions? Yes?
Actually, can you go back to this slide which you had this figure? Like let's say you were saying like for these parameters that you had the advantage in learning state.
Just, I don't know, trying to go back. Don't know what happened.
Well, maybe I can just.
Oops, sorry. No.
Yes.
This one.
I got lost a bit, sorry. So, you say that for this blue region, so this blue region is the values of Q, right? I mean,
Okay. I mean, what is plotted is
yes.
Q versus P. Basically, Q is the state parameter and P is the channel parameter. And which one is Q and which one is P? I don't know because I cannot read them.
Okay. So then, so you plot the parameter
of
the state?
Yeah, and what is plotted is this difference here.
Okay.
So basically this color scale depends, corresponds to the difference here, and one of the axes is P and one Q, but I cannot read which one is which.
Okay, I thought sorry, I didn't get what you were plotting. So there you can have the advantage, and in all the rest, I mean, what I'm trying to understand, like quantitatively, what it means. I mean, for instance, there are these regions that it's red, let's say, or green or yellow.
Yeah.
What does it mean for exactly that? I'm sorry.
I think this difference, I mean, there is
so the
some color scale here, which I cannot read. I think wherever this becomes negative, we get an advantage. And somewhere here it should become negative.
Okay, so as long as it's positive, I guess.
Then we don't have an advantage.
Okay, I see.
But just at some point it becomes negative if you could read the color scale here.
Okay, thanks.
Okay, more questions?
Did you have maybe some other examples, like of states and channel combinations that?
I think this was the most interesting one. I think we had one or two more.
The most interesting.
I mean, where we had the biggest violation.
Okay.
I don't remember what the other. It was some time ago.
It doesn't matter since this is the big. You chose to do the best thing.
Any more?
Okay. Thanks.
Okay, thanks.